Calculus provides a fundamental building block behind many algorithms in business analytics, ranging from optimization to probabilistic modeling. Now, the good news is that you can pretty much leave behind all of the ins and outs of the inner workings of how to do calculus back in high school or college when you first learned it, because for the most part, the technology exists for us to get to the results of having to do calculus operations without having to remember most of the tedious tricks that were required if we needed to do these things by hand. So let's learn about calculus and how it's applied in business analytics and how we can just get it done without having to refer to tables of integrals or derivatives or any sorts of crazy things like that. So fundamentally, calculus is about two operations on functions. The first is integration, which is finding the area underneath some sort of curve, and the second is differentiation, or taking derivatives, finding out how curvy a particular curve actually is. Let's start out by talking about integration, because that's what will be most immediately useful when we apply this to probability modeling. So when we talk about the area under a curve, what we really refer to is the area between that curve and the x-axis, that horizontal axis. By convention, what we do is we refer to the area that is above the x-axis as positive and the area below the x-axis as negative. So it's possible when talking about the area underneath some sort of curve, between the curve and the x-axis, that we can get an area of 0, because those areas can cancel out with each other. So when we do talk about areas under curves, there's some convenient mathematical notation that we're going to use just to streamline the discussion, and that is to use the integral sign. So the integral sign is like a long stretched out S. We see a number or a letter at the bottom, a number or a letter at the top that lets us know the endpoints of the curve where we're calculating the area. And then we say, well, what's the name of our function, f of x, that we're using to calculate this area? And we put a little placeholder at dx to let us know that, hey, this is a function with respect to the variable x. And in probability theory, it's really useful to do this because a lot of our probability distributions tend to have lots of crazy symbols that help to control the shape of our probability distribution. So we're going to abbreviate the area under the curve, f of x, between the endpoints a and b with this integral notation, just remembering that, all right, the area technically is between the curve and that x-axis. So how do we go about figuring out the areas underneath certain curves? Well, what we're going to do is we're actually going to approximate this area by the areas of a sequence of rectangles. So in general, areas of curves is a very hard thing to calculate. We know the area of a circle is pi r squared, but there's not really other formulas out there that most of us know about that let us know areas under curves. And so let's, for illustration, try to approximate the area under the curve 6 times x times 1 minus x between 0.2 and 0.4. So one way to come up with an answer, not a very good one, is to break up this area into 4 different rectangles. And those rectangles are going to have equal widths. And what they'll do is they'll go up to a height equal to the height of the function at the left endpoint. So what would happen if we summed up the areas of those 4 rectangles? Well, we know the heights of those 4 rectangles. That's just the function's value at the left endpoint. And it looks like that each of the widths of those rectangles is 0.05, the total interval divided by the total number of rectangles we're using. And so we can go and hand calculate, kind of brute force, well, what are the areas of these 4 rectangles? We can add them up, and we can get an answer of right at about 0.24. So that's a reasonable approximation, but clearly that's going to be a little bit too small because the areas of those rectangles miss out on some of that area between that curve and the x-axis. So what can we do? Well, we can increase the number of rectangles that we're looking at. With 4 rectangles, we can very clearly see that we're missing some of that area. What if we go ahead and bump that up to 10 times the original number of rectangles? Let's do 40. Well, here, if we look at these rectangles, we see that we cover almost all of that area between 0 and zero point 0.4 underneath that curve. We're still going to be missing a little bit of it, but if we sum up the areas of all of those rectangles, taking the width of each of those rectangles, it's all the same value, times the height of those rectangles, just the function's value at the left endpoint, we're going to get an even better approximation to that area. So let's add in even more rectangles. Let's do 100 times our original number of bars, so 400 in this case. Well, at this point, these rectangles are so skinny that just the outline of the rectangles are overlapping to make the appearance just black here. It looks like we've come up with a very good approximation to what that area is with just a whole bunch of rectangles. And in this case, it works out to be just under 0.25. And if you're thinking that that's a pretty darn close approximation to what the right answer is, well, you're right. So whenever you find yourself in a problem in business analytics where you're summing up a lot of little things, well, very often calculus and integration specifically is where you're going to end up. So let's see how this exact result, the exact value of the area underneath the curve, emerges for a bit of a simpler example. Let's take the classic example where we're looking at the curve f of x equals x squared. So the height of the curve at any particular value of x is just the square of that value of x. And let's try to approximate this area by a sequence of rectangles. Now, I'm going to keep this fairly generic, and so I'm going to say that we're going to approximate this area with a total of n different rectangles. Now, if we want to get the area between x equals 0 and x equals to 2, that means if I have n different rectangles, the width of each of those rectangles is going to be 2 over n. So I can use as the heights of those rectangles. In this case, the height of the function at the right-hand side of those rectangles. And I can see, well, what does this approximation for the area look like? And what happens as I increase the number of rectangles, as I let the value of n get bigger? Well, what I'm going to do is to write out my integral formula for this area, the integral from 0 up to 2 of the function x squared dx. I'm going to write that approximately as the sum of the areas of all these rectangles, and I'm going to use summation notation to do this. So I have a total of n rectangles, so for I equals 1 to n, let's go ahead and figure out the area of rectangle I, and then sum them all together. Well, the width of each of those rectangles is the 2 over n, and the height of the rectangle, well, I'm going to take that to be the height of the curve at the right-hand side of that rectangle. So that just means that for rectangle number I in this sequence, the height of the curve at the right-hand side is going to be 2 over n times I squared. So I can approximate this area by just taking the sum from I equal to 1 to n of the quantity I squared, and then multiplying that by 8 over n cubed, dragging out those constant terms out in front of the summation symbol. So what can I say about this sum, and what about its behavior as the number of rectangles, n, starts to get bigger and bigger? Well, it just so happens that the sum of the squared integers from I equal to 1 up to some value is a pretty well-known sum. 1 squared plus 2 squared plus 3 squared, 1 plus 4 plus 9, etc., up to n squared. Turns out to have a nice closed form expression. It turns out to just equal to n times n plus 1 times 2n plus 1 over 6. And you might have proved this in mathematics class with induction. But it's useful for us because we can just replace that sum with the exact value of that sum, the formula for that sum, do a bit of simplification and cancellation, and what we find is that our approximation for the area under that curve is 8/3 plus 4 over n plus 4 over 3n squared. So if we want to improve the quality of our approximation, just to increase the number of rectangles that we have in our approximation, making n get bigger, we can see that those second two terms are going to get smaller and smaller. 4 over n is going to get smaller and smaller and smaller as n gets bigger, and 4 over 3n squared is going to get smaller and smaller and smaller even quicker. So as I let n veer off to infinity, as I start to consider an infinite number of rectangles, I find that the area under that curve is going to converge to 8/3. And so the exact answer in this case for the area between 0 and 2 under the curve x squared is 8/3. And if you repeat this process with different polynomial functions like x cubed or x to the n, you find a fairly similar pattern that actually allows you to evaluate what the exact areas are by looking up these things on a table or maybe referring to some sort of software. Now, what we're not going to do is worry about, okay, well, what are these rules we have to memorize? What are the integrals of some very common functions? Because what we're going to do is we're going to rely on software. So long gone are the days where we really have to memorize common integrals, where we have to memorize the properties of how integrals work. As long as we kind of know how to drive the car, I'm not too concerned with the specifics of how the engine, how the gear shift works. So how are we going to do calculus in this class? Well, we're going to head on over to Wolfram Alpha, which is an extremely useful software for doing calculus and algebra really just in general. So how are we going to use Wolfram Alpha to do integration for finding areas under the curve? Well, we're just going to speak to it like we were speaking to our friend about taking integrals. We're going to say, hey, Wolfram Alpha, go ahead and integrate this particular function. We can go and transcribe that function. And we're going to give it the limits of integration from x equal to 1 to x equal to infinity in this case. So we don't even have to write that placeholder, that dx, that lets us know, okay, well, what is this a function of? Because if we write the from kind of syntax for Wolfram Alpha in terms of that variable, then it automatically is going to figure that out. So integrals are going to be no problem doing Wolfram Alpha. And in fact, R has some pretty powerful commands that will allow you to approximate the value of an integral with some sort of numerical techniques. So the name of the function that you'll use in R to do integrals, no big surprise, is just integrate. So one strategy is to define a function, say f left arrow function of x, transcribe what the formula for your function is in curly brackets, and just say integrate f lower equals whatever your lower bound is, upper equals whatever your upper bound is. It can even handle infinities. You just have to know that the abbreviation for infinity in R is INF with a capital I. Now, my favorite shortcut, though, for doing integration in R is to write the function anonymously. Don't shoot it into the global environment because it's probably just going to be a one-time use function anyway. As the first argument of integrate, we can just say function x, and then transcribe the formula for our function, and have that be the entirety of that first argument. And it's going to figure out what you mean by that, and it's going to come up with an approximation for that area under the curve. Now, one nice thing I do like about R's method is that not only does it give you the answer, its numerical approximation, but it lets you know how far off that approximation might be. So it lets you know, hey, this integral is equal to 2.67, etc., with an absolute error no more than 3 times 10 to the minus 14th, so hardly any error whatsoever. Now, the other main task in calculus is taking the derivative of a function. And when I think about it, taking a derivative is just a fancy way for coming up with an idea of how curvy that curve is at any particular value of x. So technically, the way that we figure it out is to figure out, okay, well, what would be the slope of a tangent line to that curve at the value of x? And so what we can do is to figure out what that slope approximately is equal to by looking at the function's value just a little bit bigger than at the value of x, subtracting off what the value of that function is at x, and then dividing by that difference in x's at which we're evaluating. So in general, the slope is the change in y, the change in height of the curve, divided by that change in x. The change in y is just the difference in our two function values at x plus a little h minus f of x. The amount of change of x that we considered over that range is just x plus h minus x, or just h. And we're going to see, well, what happens when we let that difference get smaller and smaller and smaller. So in the limit that the h value goes to 0, we can potentially get an expression for what the derivative of that function is at that particular value of x. And once again, the derivative is really just letting you know how curvy that curve is at that value of x. It lets you know how steep the slope of the tangent line would be at that value of x. If it's very steep, it's curving up really quite a lot. If we have a derivative that's close to 0, it's not very curvy. It's getting fairly close to looking like a straight line. So why does this formula work? Well, we're essentially zooming in this case, considering smaller and smaller and smaller differences between x and kind of that small little h where we're going. And if we zoom in close enough for a small value of x, well, it looks like, at least locally, this line is, pretty straight. So what we can do is just say, well, that looks like a pretty straight line as is, so just get the value f of x a little bit above that value of x here, x plus h. See what that change in the function's height is, divide by that change in which we move, the change in x, and that's going to give us a pretty good approximation for what the slope of that tangent line is. Just let that little h get smaller and smaller and smaller, so we're essentially zooming in as close as we can onto that curve, and we get a pretty good idea for what the derivative of that function is. So what are we going to use derivatives for in our class? Well, it's very useful for figuring out where the mode of a continuous random variable is, basically where that PDF peaks. The peak is going to be where that derivative is equal to 0. But in general, we use derivatives all the time in optimization. So we use derivatives to figure out what the maximum or the minimum value of some objective function is. And so derivatives are a business analytics practitioner's best friend. The nice thing is, though, we just don't have to worry about going through the motions and actually manually calculating what the derivative is, taking this limit, because software exists to do this for us. There's some useful derivatives to remember. If you have a flat line, a constant, the slope of that tangent line, of course, is going to be 0. It's a flat line. The derivative of that function is 0. And the derivative of a polynomial, x raised to the n power, pretty easy trick to remember what that derivative is. If you have a function x to the n, then when you take that derivative, that power comes down in front of the x, and then you subtract 1 off from the exponent. So n times x raised to the n minus 1. Pretty much the only two things you would need to commit to memory. The only thing that you would really want to be responsible for is realizing that, hey, not every single function actually has a derivative at every particular value of x. So if that function is discontinuous, if it makes a jump, we're not really measuring what the slope of the tangent line is at that value of x. There's really no slope of the tangent line, I don't think. And likewise, if we have a very sharp change in curvature, like the absolute value function, where it's heading down and then all of a sudden decides to go back up, technically at x equal to 0 in this case, there's no slope of the tangent line there. We could put in a whole bunch of different lines and have it just barely kiss the curve right there. So it's not defined at places of discontinuity or sharp turns. So how does Wolfram Alpha let us do derivatives? Well, we have a few different options. We can either start out our command with diff, short for differentiation, and just type out the function that we want to take the derivative of, or we can just type out the word derivative. Now, I tend to like actually typing out the word derivative because if you notice, Wolfram Alpha says, okay, I kind of know what you mean when you type out diff, but I'm going to assume that diff is referring to the derivative. So save yourself some time and a little bit of wondering, hey, does this warning sort of matter, by just typing out derivative. So what do we do if our function has more than one variable in it? We might run into the case where we're trying to model a pair of random quantities. So in our linear programming under uncertainty example, we wanted to come up with a probability model for the profit that we would get for a barrel of crude oil and the profit for a barrel of gasoline. And we saw that they were very related to one another, so we really should come up with a probability model for combinations of those values. So in this case, we would have two different variables, the price of oil and the price of gasoline, and so our function involves two different quantities. So we can take the derivative with respect to just one of those quantities by taking the partial derivative. We slightly change our notation from d's to kind of fancy d's to denote that, hey, this function is containing more than one random quantity or more than one variable. And it lets us know, well, pretend that other variable is a constant, treat it like a number, and take the derivative just with respect to that one value. We can also take derivatives of derivatives. So the second derivative of a function is just the derivative of the first derivative, and we have some notation for that. So the way we kind of talk about what order of the derivative that we're referring to, the second derivative, third derivative, is we put the number up in front, or up as kind of looks like an exponent to that d, and then in the denominator we use that same exponent after the variable that we're using to do that derivative. So how are we going to use this differentiation, this derivative in R? Well, what we can do is to use the function grad. So grad is actually short for gradient, which is a much more complex idea in calculus. If you have a function that has more than one variable and you want to figure out, okay, how curvy is that function with regards to all of the variables in that equation, well, technically you get the gradient, which provides you a vector of derivatives. For our purposes, really what we're going to worry about is just sticking with functions of one variable at a time, and whenever we have a more complex case, to just ship it off to software here. But grad will do the first derivatives for us. Now, it won't come up with a formula, but it'll come up with a numerical value for what the slope of that tangent line is if we just plug in the name of our function and the value at which we want to be evaluating that derivative.